Welcome, welcome, welcome to lesson 11.1. Starting chapter 11 is, of course, more inference. That's all we're going to be doing from here on out. And this looks pretty familiar. Hey, inference for means, didn't we just do that in chapter 10? And the answer, of course, is yes, you did. However, we're going to do a little tweak, a little change. We're going to kind of go out of make-believe land and go into something that's kind of more valid in the real world. So, previously, we've been giving you sigma, right? The population standard deviation. Well, most of the time in statistics, we don't have parameters. That's why the class, again, is called statistics and not parameters. So it's unrealistic in most situations to have sigma, right? There are those times we're talking about things like dice or cards where we do have the ability to get add some parameters. But most of the time, that's not the case, right? We're studying, say, human beings. We would not be able to get at the true parameter. And that's why we use statistics. So usually sigma will be unknown, which means instead of using sigma, we will have to estimate sigma with a statistic, also known as, of course, S, which we learned about way back when we talked about the two different standard deviations. Okay, so it's a very slight change, and you'll see that, it's not that bad to work with, and you'll hopefully find that chapter 11 is a lot like chapter 10 if you did well on chapter 10, and if you didn't, well, here's a second look at a lot of the same stuff. Okay. All right, so this is what we've been doing, right? The Z statistic. The problem is the Z statistic has a sigma right there. And of course, as we just said, we don't really have sigma a lot of times. So we replace sigma with the statistic for sigma, which is S. And so this piece of the puzzle down here, instead of the standard deviation, we call that the standard error. And we just use S instead of sigma. And so when we do that, remember, S is not equal to sigma, right? There's a difference. S, you're dividing by n minus 1 instead of by n when you calculate S versus sigma. So that slightly changes the distribution. So it's no longer a Z, but we've worked it out mathematically, and that change creates a new distribution that's quite similar to the Z distribution, especially for large sample sizes. And that distribution we call the T distribution, okay? So we call that a T statistic. Okay, here's some information about the T statistic. Since we are dividing by n minus 1, right, to calculate S, we say the T distribution has n minus 1 degrees of freedom. Okay, so that's some vocabulary. Make sure you pick this up, degrees of freedom. So we're going to talk about that more and more. And then also, as I mentioned, as our sample size becomes larger and larger and larger, the difference between n and n minus 1 becomes smaller and smaller. So as n goes to infinity, the T distribution becomes the normal distribution, right? It approaches the normal distribution. Okay, some vocabulary. We've talked about this idea of things that are robust versus not robust way back at the beginning of the course, right? Remember, we said things like mean and standard deviation are not robust, but we said something like median is robust, right? Well, how robust is the T statistic? It depends a little bit, a lot on sample size. And it also just kind of depends on how non-normal your data is, okay? So as long as you have a large sample size, and we can say, oh yeah, central limit theorem, or we have data that looks to be fairly normal, the T statistic is actually pretty robust, right? You just have to be careful about outliers and skewness for small sample sizes. Okay, and we'll talk about that in a minute. So this is what a lot of people have been asking. Well, when does the central limit theorem kick in? Like, what's the magic number? Blah, blah, blah. Well, here you go. We're laying it out right here. So you can use the T procedure when we meet 3 criteria, the same 3 we've been talking about, right? Good unbiased data. So if our data is collected, for example, from an SRS, that's good. That'll work. Okay. Our population needs to be at least 10 times the size of the sample because if you look back, right, again, we're dividing by the square root of n. So we can only do that if our population is at least 10 times the size of the sample. And now, here's where we're talking normality, right? Central limit theorem. When we have a small sample size, so something that's less than 15-ish, okay, we need to look at the data and make sure it's fairly normal, right? So graph it, be quite aware if there's any outliers, if there's, skewness, because that can have a big impact on the T procedure if it's a small sample size. Okay, next, if we have kind of a medium-sized sample, so we'll say 15 to 40, things are going to go pretty well. Central limit theorem's really starting to kick in. So as long as we don't have any real strong skewness, we should be safe to go. Okay. Once we hit a sample size of 40, we're going to say central limit theorem pretty much assures us normality. Okay, that's what we've been saying all along for a lot of sample sizes, but we now have a number on it, 40. And now, these are not hard and fast numbers, right? There is no, theory of statistics that comes down and says 40 is way better than 39. No, it's just, these are kind of guidelines, right? Think small sample size, medium sample size, large sample size, okay? And these are guidelines. Different books and different people have slightly different guidelines. So don't get too hung up on these exact numbers. Just think kind of small, medium, and large, okay? And these, I believe, are the numbers that came from our textbook. Again, other books might have different numbers. Okay, before we get into a calculation, we didn't really talk about the matched pair z-test, but that is fair game from chapter 10. It's just that chapter 10 is already pretty overwhelming for students, so we didn't go there. But there is a matched pair z-test as well, and that's fair game for the AP exam. But today we'll talk about doing a matched pair t-test, and we'll do some other matched pair tests down the line. Okay, so you might recall when we talked in chapter 5 about designing experiments, we talked about, hey, sometimes we'll do a matched pair test, right? So anytime you have an experiment that's designed as a matched pairs experiment, we're going to have, right, a pair, so two treatments. It could be a placebo and a treatment, or it could be 2 different treatments, right, on the same person. What we do is, rather than having 2 sets of data, it makes more sense to just subtract the 2 readings. Okay, and so once you've subtracted those 2 readings, we actually have just 1 set of data. And that's how a matched pair test works. You just look at, well, what's the observed difference between the 2 treatments, right? The null hypothesis would be there's no difference, right? The average difference is 0, and then the alternative could be one-sided or two-sided again, depending. Okay, so that's how you do a matched pair test, t-test, z-test, whatever. You just subtract the 2 readings, and then you look at, well, what's the difference? Is there a difference or not? Okay. We will do confidence intervals and significance tests today, all in the same day, since you have supposedly mastered those ideas. So the confidence interval, again, SRS, population at least 10 times the size of the sample, normality. It's X bar plus or minus our critical value, but it's now a T value because we're using S instead of sigma. So just kind of remember that Z and sigma go together, T and S go together, right? You can't mix and match. Once you go to S, it's a T. Okay, if you have sigma, it's a Z. Okay, other than that, everything else is the same. All right, let's try an example. And this time I've purposefully gone with data instead of statistics because I have a very small sample size, which means if I didn't have the data, how can I check for outliers? How can I check for normality, skewness, and all that? Okay, so here's what we do. When we have our data, before we do any of the inference, we need to take a look. What's the sample size? In this case, 1, 2, 3, 4, 5, right? My sample size is pretty small. It's only 5. So I better check to see if this data has any outliers. And really with a sample size of 5, the only things we can kind of check for are outliers and make a normal probability plot. Sample size of 5 is too small to get anything out of a histogram or a stem plot, right? As my data set gets larger, then the histogram and the stem plot kind of start to work and make sense, because you can see normality on those with larger sample sizes, but not with a sample size of 5. Okay, so enter the data in the calculator, which I did. Okay, and first thing I like to do 2 things, but the first, how about we take a look at the modified box plot? Because the modified box plot will tell us very quickly if there's any outliers, right? Oh, something went wrong. Oh, the frequency. I have no idea how that happened. Okay, so there's our modified box plot. So there's no outliers. Now, skewness, again, there's 5 pieces of data, right? So it's kind of hard to see skewness with only 5 pieces of data, to evaluate it, right? So I can see there's half the data, there's half. It looks like, the left half has more spread, but for 5 pieces of data, it seems kind of reasonable. So basically the main thing here, I'm looking for, are there outliers, and is there heavy skewness? But with 5 pieces of data, the whole heavy skewness thing's kind of hard to read. So that's where the normal probability plot comes in. So there's my normal probability plot. Is it perfectly linear? No, but it's reasonably linear, again, for 5 data points. So I would call this acceptable, but it is a very small sample size, so be careful. Okay, now the other checks. We don't know what's the population, right? We don't know where this data came from, what we're performing inference on. So we'll have to assume there's at least 50 members of the population. And we're also going to have to assume that the data came from an SRS. So assume an SRS was used. If another method were used, it could invalidate our calculation. Okay. And then we're also going to assume the population contains at least 50 individuals. So we can safely use the standard error formula. Okay, so first thing we're going to do is the 95% confidence interval. So x bar plus or minus critical t star, times the standard error. So step 1, we need to get the mean. So remember, one variable stats, we can do it that way. There's my mean. Now, the critical t, this can be read from your formula sheet. So please make sure that you bring the entire formula sheet to the test, okay? T values are found, I showed you this when we talked about, right, here's the T distribution, table B. I showed you this when we talked about confidence intervals the first time around, right? I said, hey, at the very bottom, we can find a lot of the most common confidence levels right here. And then if we go to the infinity row, there's the Z star, because this is a T distribution. And once n goes to infinity, you have, yes, the normal distribution, a Z. So that last bottom row, those are Z stars, okay? The rest of the table, those are T stars, okay? So if I want to do a 95% confidence, okay, and my n is 5, okay, my degree of freedom, as we mentioned, is n minus 1. So my degree of freedom is 4. Okay. Now, you'll notice the page with the confidence level starts with the degree of freedom of 21 and then goes down to infinity. So I got to go back to the previous page. Okay. On this page, I can find the degree of freedom is 4 right here. Okay. But at the bottom of this page, it doesn't say confidence. So you, as the reader of this table, need to be wise enough to understand a 95% confidence has a tail probability of 0.025. This is the column that represents a 95% confidence, right? Because remember, a confidence is two-tailed, and this is if you look at the picture, this is a one-tailed, and it's, by the way, a right-tailed test, right? Our table A is a left tail. Okay, so that's the column I would be reading to get my critical T. And for a degree of freedom of 4, because our sample size was 5, there's my T right there, 2.776. So that's where the 2.776 came from, okay? The 20.741, well, that came from our one variable stats right there. And then square root of 5 finishes off the standard error. So again, this part right here, that's the standard error. So just vocabulary. Okay, and then the whole piece, that's the margin of error. Okay, so that term didn't change. And there you go. There's our 95% confidence interval. So make sure you always complete your confidence interval with a sentence, right? We are 95%, right? You always have to state the level of confidence. The true mean. And then you would put in whatever context you have. In this case, we don't have any, but normally we would say the true mean of blah, 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 blah is between. And there you go. So mainly review is just finding your T star and using S instead of sigma. That's the only difference, okay? All right, and again, don't forget on the test to put context. Very common mistake to leave the context out. There's just no context in this problem, so. All right, let's repeat. And let me cover that up. Try it on your own. This time do a 90% confidence. So basically I'm asking, can you read the table successfully? So that's kind of what we're gonna do there. So pause, find the correct T star for 90% confidence. Okay, so 90% confidence, that means you'll have 5% on each tail, so your tail probability would be 5%. So right there, 2.132 is the T star for 4 degrees of freedom and a 90% confidence, right? And again, maybe I'll make a drawing because I know there's always some students that struggle with this. So if this is 90%, right? 5% on each end. So that's why a 90% confidence will correspond to a 5% one tail probability, right? This is tail probability, one tail, see? So that's 5% there. Okay, all the other numbers remain the same, and all the checks remain the same, and there's the new confidence interval. Okay, so we are 90% confident that the true mean lies between 24 point blah, 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 and 64 point blah, blah, blah. Okay, I didn't write it out because we already wrote that on the previous slide. The whole point of this slide was, can you find that T star? Okay. All right. Let's cover that up. Let's try another example. This time we're going to give you stats instead of the data. All right, the average CHP fine is reported to be $350. You suspect the average is higher than that. So you sample 12 victims and you find a mean of 358. Well, there's your X bar, right? The sample standard deviation, notice sample, so that tells me S. And once I see S, I know, hey, I'm going to be using T. All right, let's do a 90% confidence interval, and then let's do a significance test. Okay, so our 90% confidence, we just looked that T star up, okay? Except we now have a sample size of 12, okay? Sample size of 12, that means a degree of freedom of 11. So we know which column we're in, right? We're in the 90% confidence, which is a 5% tail. But we got to read all the way down here to degree of freedom of 11. And notice as you read down the table, the numbers become smaller, as they should, right? Because our variation is decreasing as our sample size increases. Okay, so there's our T star, 1.796. So we're going to put that in along with our 358, our 16, and our square root of 12. Oh, that's another common mistake. This is n right here, right? Don't put in n-1, right? The n-1 went in for calculating S. You don't double it. You don't do another n-1 a second time, okay? That's a common mistake. So it's S divided by square root of n. All right, working that out. There we go. So again, we are 90% confident. The true mean CHP fine, that's California Highway Patrol, for those of you that didn't know that, is between $349.71 and $366.29. Okay. Oh, we should do our checks here, right? It says you sample 12 victims, so I'm assuming you used an SRS. You should know to do that as a statistics student. So assume an SRS was used. If not, it could invalidate our calculation. Okay. Now, there are certainly at least 120 victims of the CHP, so population is clearly large enough. So it is safe to use our standard error formula. Yeah, okay. Normally we, of course, do that first. So put that on top, and then there's the calculation. All right, so there's our confidence interval. Now, let's do a significance test here, okay? And then we're going to talk about how those two things relate. All right, so step one, notice we haven't used the 350 yet, right? because that's your null hypothesis right there. 350 is H naught. Okay, and notice we think it's higher, so there's our alternative hypothesis. Okay, let's jump on that down there. So null hypothesis, the average finds 350. Alternative, it's more than that, right? Higher. Get our t the same way we would get a z. So x bar minus, in this case, s, the estimator of sigma, okay, over the standard error. Okay, so we get this t star. Now, how do I get a p-value from that t star? Well, table B is not the greatest. It works. It'll give you a window of accuracy, but it's not going to give you an exact p-value, right? Because there's just so many rows. So I go to degree of freedom of 11. I read across, and oh, I'm between these two entries, which means if I go up to the top, I must have a probability between these two values. So my probability is somewhere between 5 and 10% for a one-tailed. And that's exactly what I'm doing, a one-tailed. And that's as accurate as I can get with table B. Okay, so, and it's perfectly fine to say, hey, my p-value is between 5 and 10%. That tells me the level of evidence that I have, right? It's, you know, kind of moderate evidence. It's not super strong, but there could be something there. Okay, now, if I want to find the exact p-value, well, that's where I can use my calculator, okay? So I'll show you two ways. We've been using the normal CDF. Well, guess what? There's a T-CDF as well. So if you scroll down there, oh, look, also an inverse T. But anyway, scroll down there, T-CDF. Okay, my lower bound, I can do this in terms of the T, 1.732. And I think, I'm not sure if I just put in the degrees of freedom or not. Nope. Okay, upper bound, and then the degree of freedom. Okay, so there's the accurate p-value from our calculator using the T-CDF. Okay, now the other option, I mentioned there was two, we can go to test, and hey, look, there's a t-test right there. And in this case, I have the stats. Null hypothesis was 350. X bar was 358. And 16. This time n was 12. And we have a one-tailed greater than. And there you go. It'll spit out the t and the p-value both. Okay, but again, you've got to show work. You've got to show this work right here on a free response question. If you just write the calculator printout, you're not going to get full credit. Show that work right there. Okay? All right, now, one other thing I wanted to mention. You shouldn't be surprised by that p-value of a little over 5%. Here's why. If you guys are kind of making the connections and putting things together in your brains, you would have noticed, here's my 90% confidence interval. And my cutoffs were 349.71 and 366.29. So instead of, we could have compared our T to our T star, right? There's the T star, 1.796, and our T was 1.73, right? So that's one thing I could have done. I could compare those two and say, huh, I didn't quite make it. I needed to hit 1.796 to have a tail probability of 5%. Right, assuming we had a 5% alpha. Okay, or I could have compared my 350, my null hypothesis, right, to these two boundaries and said, oh, 350, it's close, but it's inside my 90% confidence, which means it's not out in the 5% tail. Right, so that's how these things work kind of together. They're oftentimes really the same thing. And it's perfectly valid, by the way, on the AP test to calculate this 90% confidence interval and then point out, well, the null hypothesis of 350 is inside the interval. Therefore, there's not enough evidence at a 5% alpha to reject the null hypothesis. Okay, that's allowable. And as a matter of fact, I usually ask you to do that on a test question or more than one over the, inference units. So make sure you understand how you could use the confidence interval to answer a significance test question. You may as well, if you've already done the work, why do more work, okay? But you can see the work gets you the same result, and it gets you that nice accurate p-value. So that's one of the reasons to continue the problem, because, hey, is it close to 5% or is it closer to 10%, right? That kind of window of, I know it's not there, but, right, there's kind of a big difference between this and like 9.9%, right? Okay, so hopefully that makes sense. And hopefully inference is getting easier for you and making a lot of sense, because we're going to keep doing inference. Thanks for tuning in.